It's not too bad, eh? Like you would take that. Tension is the force in a rope, string, or cable, and we can calculate it using a bunch of different ways. One thing I will say right off the bat is that some of you will ask me at some point, Mr. Espin, what was the formula for tension? There is no one formula for tension. You'll find that there are well over 10,000 different situations that involve tension. And in fact, there's tension that you haven't even considered yet. Like the fact that when you move, your body doesn't rip apart because there's tension in the gluons and things that are holding you together, right? But to keep it simple in the land of Physics 11, we only look at tension with strings, ropes, pulleys, things like this, right? So if you have a simple, there's water in this bucket, you have a simple situation of gravity pulling down and tension pulling up. If this is not accelerating, those two forces are equal, but opposite direction, and so this is not accelerating, and you get a net force of 0 and an acceleration of 0. And if you can calculate gravity, which this would be around 50 newtons, then the tension force is also 50 newtons. What would happen, what would I have to do to this to accelerate this bucket upward?
Increase the force of tension.
Good, so if I increase the force of tension, I accelerate and the bucket moves up. What if I decrease this? And I pull a little bit less and this moves down, like in an elevator or something, right? Which we're going to learn about later. Okay, so second situation is we've got Marco in his West Van hat here, and he's pulling a mass. He's got 98 kilos here, and he's pulling with 1,000 newtons sideways, and we want to find the tension in this first rope and the tension in the second rope. Okay, so how do we do that? This is kind of interesting. Finley's got something to say.
No, I have a question.
Okay, go.
Does it lose its original force with the second one?
Well, kind of. I'll show you how that works. Zed?
First, you're going to find acceleration.
Okay. So that's the first question is this accelerated? Yes. If you think about this whole thing, you've got two different objects, right? Eddie, can you flip the door closed for us? These two objects have different net forces acting on them. They have different tension forces acting. But there's one thing on these two blocks that is the same. And that is the acceleration. So if you're looking for something to hold on to when solving a tension problem, it's usually the acceleration. Because if two things are tied together, they have to have the same motion, right? They have to have the same acceleration. So what we do first, as Zayad presciently suggested, is we think of this thing as one big mass. Okay? That's what you do first. And we say that one big mass is how much?
148.
Good. If you add them together, your mass equals 148 kilograms. And you can think of this, right? It's got a rope between, and we'll deal with that later. But the net force on the whole thing, we should be able to find. Right? There's no friction in this case. We will deal with friction, but we're not going to do it right now. So the net force on this object is equal to how much?
148 times the acceleration.
Yes, but we know the number already, right?
Just divided by.
Because Marco's pulling on this whole thing.
Acceleration equals 1,000 over 90.
So my net force is 1,000 newtons.
Over 148.
It's not. That's not necessarily the net force on this block or that block.
Both of them together.
but it is the net force on the whole thing. Okay. And so let's give Ali the floor here. Ali, how am I gonna solve for acceleration?
Acceleration equals F net over total mass, so just 1,000 over 140.
Very good. Let's have a golf clap for Ali.
Answer is 6.
Okay, now raise your hand after this. Okay, F net over M, and he's absolutely right. This is the total mass here, right? That's gonna give us our acceleration. So we do this first. If I was gonna put this into steps, step 1 is usually finding the acceleration. Because that's the one thing that these two blocks have in common. They both have the same acceleration. So that's kind of the key. That's what links this all together. Okay, so F net over M total equals A. And if we do that, we have 1,000 newtons over 148. We said it was kilograms. And so our acceleration is 6.8 or so. We're not really worried about being super. And so that this thing, all of it, is going to accelerate at 6.8 meters per second squared. This is the acceleration. Okay, we've got that now. I'm going to erase this now. So you got the overall acceleration. And let's just draw this out just really small here. Both of those blocks accelerate at the same rate, right? Nikki, if I know the mass of this block and its acceleration, what can I calculate? Good, good. If I know the mass of that first block and I know its acceleration, I can calculate its net force, right? So let's do that for both blocks. This is 98.
Force of the one block.
Yeah, and this is 50. So we've used the total net force, which is 1,000, to find our acceleration. And our acceleration was somewhere around 6.8. So we know that, and we're going to keep that handy, because we know both individual blocks have to accelerate at that rate. Okay, and so we use that, and we go F net on the 98 kilogram block is equal to mass times acceleration. And so that's going to be 98 times 6.8. 670 something?
960.04.
Did I say 700?
Yes.
Sorry.
960.4.
661.5.
Yeah, it can't be 900 or something.
Yes, it's 960.
Dude, take your calculator, punch it in.
98 times 9 point. Oh, it's 6.8.
Yeah, 6.8, no 9.8. I was like, am I going crazy? 662 or something? Okay. So about 662 newtons. Now that, take note, this is not the net force on the whole thing. It's just on this block. Okay? Does that make sense? Okay.
But it would be 666.
Can you just minus it?
It's not 600.
If you keep all the decimals, you get 662. It's okay if you got 666. It's evil.
Wait, why would you
Don't do it!
Why would you subtract the force applied minus the force of tension?
Well, we haven't got there yet.
Oh.
We haven't got there yet. Don't. We're just doing the net force. Okay, so let's do the 50. I'll do this one in green. Let's find the net force on it as well. So we'll do the net force on the 50 kilogram block. That's also MA, but of course it's a different mass. So 50 times 6.8 is
340.
340 or so.
Exactly 340.
Okay. 340 newtons. Now that's the net force on that block. So notice these two masses, they have different net forces acting on them. Okay. Okay. Let's do now a free body diagram of each block. Okay. This block here, the 98, it's being pulled forward by what force?
Applied force.
Force of tension, and it's going to be the same as Marco's applied force of 1,000 newtons, right? So this is 1,000 newtons out the front. You okay? Did it break?
Oh my god, he's going into labor.
Is it glass on the inside?
No, it's
That was pretty good. You said that. Yeah, nice, Eddie. Eddie's gonna go on tour. There is some force of tension back, right?
Would it be just?
Did it? Get there. And this is gonna be the second force of tension. Okay. So let's calculate what that would be. If our net force, and this is gonna depend a little bit. Well, actually, you know what? I'll do that on another board because we need more room. Let's draw this free body diagram here. What's the forces acting on the 50 kilogram block?
Applied force 1,000 newton.
Is there 1,000 newtons pulling on that block?
FT2.
FT2, and anything backwards? Nothing. The tension in this rope, so this is our FT2 and this is FT1. The tension on this rope is different. We don't know what it is yet, right? And it's pulling this 50 kilogram block forwards. There is no force backwards. Everybody got that part? So I just want to do this. I'm doing this as your first one, so we're kind of like, let's slow down and do it. Like, you'll do this faster later, but just want to kind of make sure we get it straight from the beginning. Okay, so let's do our two blocks. I'm just going to draw them again. Our 98 has these two, and our 50 kilogram block has this. Now, the net force here was 662, wasn't it?
Yeah.
And this one is 340? Okay. Let's do this block first, if you'll indulge me.
Why did you say?
If the net force on this is 662, and we're trying to find that, and this is being pulled with 1,000 newtons, how would we find that component of force, Marco?
FA minus FT2 is equal to 662.
Interesting. So if you're a real world thinker, you're gonna go like Marco and you're gonna say, well, these two are competing. It's a tug of war, and the 1,000 newtons is gonna win. And how much is it gonna win by?
The difference.
This much, right? The net force is how much you win by. So he's gonna say this 1,000 minus the other force equals that, right? So there's a real worldy way. And the real worldy people are gonna say 1,000 minus FT2 is equal to 662. So this is your net force. And your 1,000 is the forward force and FT2 is the backward force. And so these two compete, and that's how much they win by. If you do it the mathy way, how would you do it? Any mathy people out there? So yeah.
Net force is going to equal to the 5 plus force of tension.
Good. So this is, now I'm gonna give something away here. What else could we call this 1,000 newtons? This is FT1, right? When it's acting on this block. Marco's pulling the rope with 1,000 newtons, and on the other end of the rope, it's pulling the block with 1,000 newtons. And those two tension forces are gonna be equal. So on the block, we call this FT1 and that's FT2. They're two different tension forces. And so we would have to add those together to get our net force. If I want to solve for FT2, how do I do it? What am I subtracting, Finley? Oops. Yeah, I just subtract this over. It's the same in the end, right? Looks like the same as this. So you're gonna have 1,000. Oh, that's not 1,000. 662 minus FT1, which is 1,000, is equal to FT2, and that's going to be negative 338 or so.
Should you go 1,000 first?
Now, if you're thinking, that's strange, it's weird, it's okay. Look at this one. If that 50 kilogram block is being pulled by only one force, the net force has to be the same as that one force, right? Does that make sense? Because the net force is the sum of all forces, and if there's only one force, then the net force has to be the same as the one force. So if there's only one force here, and we know the net force, then how much is that one force? It's got to be 340, right? So we just say here, FT2 is equal to my Fnet, and so FT2 is equal to 340. Now you'll notice that these two are slightly different, but that's just due to rounding and calculation in your calculator. There's another big difference though. What's the other big difference?
The direction.
Yeah, one is negative and one is positive. Is that okay?
Yes. There's no friction.
Yeah. So there's no friction. We don't need to worry about that. This one is going to the left, which we've said is forward. And this one is going to the right, which we've said is backward. So it makes sense that this one is negative and that one is positive. Because on this rope, at the 50 kilogram block, the rope is pulling forward. At the 98 kilogram block, the rope is pulling backwards.
What?
So on one rope, if there's a rope joining these, the tension forces at the two ends will be equal and opposite. Always. Okay. Somebody had a question back there. Ali K, you got a question? You alright? Yeah. Okay. If you take the net force on this block and the net force on that block, what do you get if you add them together?
1,005.
Which is the net force on the whole thing, right? So the two net forces on the blocks have to add together to get your total force. Yes.
So in all situations, the second one would be like FT2 equals Fnet?
No, if I have friction, then friction is going to be pulling back on this guy.
Is it only if you have friction?
No, it can be other things. If I have a giraffe pulling backwards on this, or a jetpack, or a magnetic field, or any number of other things. But if you're on a frictionless surface, and that surface is flat, and there's only a rope pulling, then there's only one force. Madison.
If there was friction,
Yeah.
would there be a force backwards on the second block, but would there also be a second force backwards on the first?
Yes.
How do you deal with that?
I will teach you that, but not right now. I might possibly say the force of friction is a certain amount on this block and a certain amount on that block. Or I might say there's only friction on this block, but that one's on a patch of ice and so it has no friction. Something like that. I will teach you how to calculate those forces, but that's in the next unit. So you don't have to worry too much about that. Yes, Sam?
On the first block, the net force for the entire block is 662, right?
Mm-hmm.
And then the force of tension on the first string is 1,000 newtons.
Mm-hmm.
And then
Carry on.
it's just the first block's really confusing me. With
Yes.
The force applied and the net force is
I understand that confusion. It's a good one. It means you're thinking about it. Everybody put your hands like this. One of your hands, let's say this one, is being pulled at 1,000 newtons, right? If I just hold this hand in, if I'm just being pulled at 1,000 newtons, am I going to accelerate at 6.8 or more? More, right? But I'm not accelerating at more. I'm only accelerating at 6.8. So what else do I need?
another force pulling me back.
I gotta have this way. So I've got 1,000. This is big, and I have a little tension force pulling me back because that block behind me is dragging me backwards, right? So I'm being pulled. I'm moving, but not as much as I would be moving if I dropped that other block. What would happen if I cut the string between these two? Keon?
F net would be 1,000.
F net would be 1,000, and what would happen to that block?
The force on it would be 1,000 newtons.
Yeah, and what would happen to its motion?
So
It would get faster, like it would accelerate even higher, right? You'd be getting dragged along like this, being pulled back and all this, and then it would be like, and then you'd be like, woohoo, right? And it'd be, so yes, you're being pulled with 1,000, but you're being pulled back with 340. That makes a net force of 662 on this block. It's just kind of a tug of war. And what's left is 340, and this block gets pulled with that 340. Yes, Max?
How do you find out how much force is needed for like the string or whatever to snap, like for it to be?
Oh, good idea. Good question. In the real world, if you're an engineer and you're holding something up with a cable, you guys need to listen to this. Hey, possible engineers, you need to listen to this. If you have a cable and you're going to use it to, let's say, steady a power pole or to hold up a balcony on an office building, how are you going to find the maximum force that that cable can withstand? Okay, so Soren said force of tension. That's true, but how are you gonna quantify that? Because Max is right. If you're actually doing this and you need to know if that cable's gonna break, like in other words, you need to know how, like, take the peak-to-peak gondola in Whistler, right? You know, you can actually go in there. How many people have skied at Whistler? How many people ski in general? Who snowboards? Wow, you guys need to get out. It's really fun. Who's been on a gondola or a sky ride or a tram of some kind? Okay, chairlift. So those cables have to be rated. Why do we need to rate them?
So we don't fall off.
So we know how much weight they can hold. If there's too much weight, it'll break and people will die, right? So how are we gonna calculate those max forces? You can go in the little hut where you go across the peak to peak, and they actually have a chunk of cable in there, and it's on a plaque, and it lists the max force per meter and all that stuff in there. It's kind of interesting. It's really easy.
Just pull the mass.
How would I do it with that string hanging there?
Pull on it.
Pull on it super hard, but how would you quantify that pull? Yes, Arsha? How do I quantify the force of gravity? So I put a little tray on that thing, and I keep loading it with mass, right? Dirt, 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 and I keep loading mass until the cable breaks, snap. And then we go, oh, okay. Now,
Oh, so you add to the force of gravity until the cable.
There's no way that's not gravity.
that's right. And you do that 100 times, and you see the average, and you calculate the uncertainty in it. Now, you need a lot of mass, like the cables that hold up the Lionsgate Bridge. You literally need like an office building to hang on that before it breaks, right? But it's a braided cable, so it's made of a whole bunch of teeny little cables that are wound. And so we break one of those, and then we multiply the force by how many are in the braid.
Yeah, but doesn't the braiding power make it stronger?
Definitely. That's why you can multiply it. And you do that with weak cables, and you see the relationship between the braiding and stuff.
Isn't there also a relationship between the surface area?
Yes, and length as well. So that's, what you're talking about is engineering, and there's a whole, well, there's like, you can literally make a career on knowing all that stuff.
Would a long
Yeah, I
string
should've
be easier to break?
Yes, in general. Ali?
So is that like two strings, like the example that you put like two strings?
Yeah,
Would the tension like be shared between?
yes, in general it would be in half. General it would be in half. There's lots of extra things in there, but if you want to, the general rule is if you have 3 strings, then you're gonna have triple the strength because you're dividing that force in 3, right? Okay.
But doesn't it have like a lot of uncertainty?
Yeah, and so would you build the cables on the Lionsgate Bridge if you knew that they held 1,000 megatons? Would you build the bridge to carry exactly 1,000 megatons? How much bigger would you make it? How much stronger?
That's why like elevators are like maximum weight like a ton. And
Yeah.
it's like how are you gonna put a ton?
Yeah,
into that?
or it usually says max 13 people or whatever, right? But the elevator's really built to carry usually double or triple what it says. So if you can put in 26, right? Because
Let's try it. Let's
They
try
haven't
that.
tested it, so.
Yeah.
It's too dangerous.
I might have tried it.
Alright.
Much according to my calculations, half of this is according.
Okay. In honor of Marco's suggestion,
According to Soren's calculation, it's probably according to
we have an air track, okay? And you have a rider on the air track.
No friction.
No friction. And let's say this is 300 grams, okay?
that's a beautiful picture.
And you have a pulley on the end. And there's a cable that goes down to a mass.
What's the big?
How much mass are we gonna have
5.
here? Let's have 200 grams. Okay, and this is no friction. Find the FT in the string. Bless you. Yes.
We don't get an acceleration. We don't have a force supply.
There's a lot to say about pulleys, but in yeah, it is a pulley,
Isn't
but
this an air
it's
shaft?
not the type that would cut the force in half. So,
Not a double boy?
I have a story for you. When I was your age, how old are you guys? Okay, when I was younger than you, when I was 14, my dad came home. He had been on a trip, and he walked in the house, and I was like, "Hey, Dad," and he never said very much to me. He was always kind of a gruff guy, and he goes, "Hey, I bought you a truck," and I was like, "Yes," and I was like, and I ran outside, and I couldn't see another truck. There was only his truck. And I came inside and I was like, "So, where's my truck?" And he goes, "It's in the back of my truck." And I went outside and he had bought from a junkyard a truck. And it was in pieces. It was like 2,000 pieces of truck. And it was all in the back of his truck. And we spent the next 2 years building that truck for me. So when I was 16, I had a truck that I had
This is a true story.
built with my bare hands. Yeah. It was an F-150. And so we had to do everything. And one of the things we did was rebuild the engine. Now, if you've ever tried to lift an engine block, it's not so easy. It's maybe 400 or 500 pounds, right? And it's awkward. Yeah, Ali G could do it. But we couldn't, but we had a block and tackle. So it was a set of 5 pulleys. Okay. And we hung it up to the rafters of our patio, which nearly pulled our patio down. But if you pulled, and I had a rope that went through there, and we hooked up the rope to the engine. And when you pull, because the rope is going up to the pulley and down to the engine, and back up to the pulley and down to the engine, back to the pulley, 5 times. What that means is that you have to pull 5 times as much rope. So if you want to lift the engine 1 meter, you have to pull 5 meters of rope. But what that also means is that if it takes to lift 500 kilograms, you only need 1/5 of the force. So it's only 100 pounds. So you need to pull more rope, which is fine with us, but it cuts the force by however many pulleys you have, right? And it was pretty cool. You could do it. You could like, and it was really right. So yes, a pulley that goes up and down to the mast and back up, that will cut the force in half. But this doesn't come down and go back up. This just goes that way, and it's attached to another mast. So it's a bit of a different situation.
Is it constant? Is the velocity constant?
You tell me, would the velocity be constant here? If I release this, is it going to go at constant velocity?
It's gonna accelerate.
It has to accelerate. Why?
9.8.
Is it going to accelerate at 9.8?
No.
No.
Nope.
It's impossible to find it.
Because the other weight here, that's right.
Add the mass.
Do you want me to just show you? Don't show it? Take a minute and try. Just try.
The camera's still on.
Yeah, should we pause it? If you're watching this video, try it. But I'll show you how to do it in the next video.